I'm Zach Cox, here to talk about CTE and metabolism. And I'm just doing some things right now to make sure that we are good to go. I'm Zach Cox, here to talk about CTE and metabolism. And okay, that was scary. I got to hear my voice. Okay. Perfect. Okay. I got everything set up on my phone, and we are ready to go. All right. So I'm here to talk about chronic traumatic encephalopathy, and more specifically how it affects the glucose metabolism within the brain. So before we get started, I'm going to talk about a little bit of background information that is required in understanding this disease, as well as understanding some important components of the metabolic processes and pathways in conjunction with the effects that disruption may cause. So what is CTE? So CTE stands for chronic traumatic encephalopathy, and in this presentation it's going to be referred to as CTE. Now what is it? It is a neurodegenerative disease. It is only found in patients with a history of repeated head trauma caused by a clumping of a protein called tau that is bound to microtubules and is important for transmitting signals, transporting different types of organelles and proteins and cellular components to and from the soma and the presynapse of the neuron. So this is an example of what the normal versus CTE brains look like. As you can tell, there's a very, very large amount of atrophy. If you look at the corpus callosum, it is actually damaged. The hemispheres are also shrunken to a very large degree, and a lot of the gray matter and the white matter it is reduced heavily. The hippocampus and the amygdala have also shrunken, which those are very important components of learning and memory and emotional control. So traumatic brain injury, also referred to as TBI. This is something that's very common with those with CTE, and it is something. It is defined as an insult or damage to the brain that is from an external source. So if you can think of like a car crash, if you hit your head, or if you watch athletes playing hockey or soccer or basketball, anytime someone experiences a concussion, that's considered traumatic brain injury. Now, these have certain effects that, like they cause permanent or temporary injury, which leads to cognitive impairment and an altered state of consciousness. TBIs are also a more advanced form of subconcussive impacts. So if you were hitting your head on a wall, or you accidentally dropped or something fell on your head, that's just a minor subconcussive impact. However, repeated small subconcussive impacts are what lead to CTE. So you're not at risk if you only experience one small one. It's the repeated subconcussive impact that over time that has been linked to the disease. So as you can look at the photo, there's so many different causes of TBI. Anything from assault, from falls, from accidents in motor vehicles. Struck by or against that is usually what constitutes sports. But yeah, the falls and motor vehicle traffic for those that are not athletes is the most common cause of TBIs in the U.S. population. So these are some of the areas of the brain that are going to be affected. More specifically, the frontal lobe, depending on where the contact has occurred, you're going to have a lot of damage in the frontal lobe, and that's going to affect your social skills, your ability to plan, to reason, and understand what's being told to you. A lot of other very important things that are damaged are areas within temporal lobe as well. So the thalamus, the hypothalamus, the hippocampus, they're going to be in like the inner parts of the brain. And as you saw in the image earlier, the corpus callosum, the structure or the tissue, the thing that transmits information between the left and the right hemisphere, that is going to experience severe atrophy. So now, tau proteins, these are very important in maintaining the structure of the microtubule. Now these are found in the axons of a neuron. And these are bound to microtubules, and microtubules are important for transporting signals, organelles, ions, and other intracellular components from the cell body to the synapse. And they use motor proteins and called kinesin dynin. Those are some two main proteins that are important for anterograde and retrograde transport. And they can also transport vesicles containing neurotransmitters like dopamine, like glutamate, things that you need to excite or have an action potential, fire, and have the neurons communicate to one another. They're also used to stabilize the microtubules. That's like their main job. So whenever these things become disengaged, whenever they fall off the microtubule is a dimer, and it's just it's held together based on chemical interactions, and these tau proteins stabilize that. And whenever they are unbound, the tau proteins are unbound to the microtubule, the stabilization of the dimer decreases, and it just begins to fall apart. So as you can see, the inner microtubule is right here, and then you have the tau protein, just long tau proteins that kind of fit into the little niches of the microtubule and the tubulin, alpha and beta tubulin, the two components. Now, apoptosis is referred to, it's programmed cell death, and it is triggered by cell signals like caspase and apoptosome. Now, these two things are released from the endoplasmic reticulum and the mitochondria whenever there's a large influx of calcium or cytochrome C or BAK or BAX. These types of molecules right here, they are the precursors of apoptosis. And now, like, whenever the old, as a phrase goes, when there's smoke, there's fire. These are the smoke signals. Once you see these in the blood or in the neuron, your cell's dying, and it doesn't have that much time. And this is a very critical component for diagnosing CTE. Is widespread apoptosis leads to a myriad of issues. So you lose the ability to think and reason because your cells are dying. You no longer have connections between upper and lower motor neurons. You have no longer have connections to different areas of the brain. And this ultimately leads to atrophy, and this is the degeneration or wasting of the cell. And it's typically caused by a lack of sustenance, more importantly, apoptosis, and then necrosis. It can also, another thing that can occur is diffuse axonal injury, and that is just stretching or ripping apart of the axon. And so this is a normal cell, what it would look like, and then this is what an apoptotic cell. So it begins to it just bursts because it's no longer able to regulate the calcium that is going inside the mitochondrial or inside the neuron, and so that calcium enters the mitochondrial matrix, and it starts beginning the cascade, the apoptotic cascade of releasing the pre-apoptosis factors into the cell, and ultimately it just makes the cell burst and then you have a dead neuron. So CTEs most commonly found in football players, soccer players, hockey, and other athletes that have high risk of multiple subconcussive impacts. So anytime there's someone that has, or anytime there's an activity in which individuals are, their heads are exposed and they're able to come into contact with one another, that's where you're going to find most individuals that have symptoms of CTE. You can also find them in military personnel who have been close to blasts, like IEDs, any types of explosive devices that explode near them and cause them to experience some form of traumatic brain injury. Accident victims are another one, so car accidents, falling in the elderly, or if someone has poor control of their motor functions and they fall a lot, they're at risk for CTE. Up to 30% of the brains examined had a prehistory of repeated brain trauma, were found to have CTE. And then this is an important statistic, and a lot of times it's just been swept under the rug, is 96% of former NFL players examined by Dr. McKee at Boston University had identified CTE. Now, all these players were deceased, but they had died at an early age. But 96% of them had CTE. So that just shows you that there's a very strong correlation between the number of head injuries that you experience, as well as the period of time that these head injuries have occurred in CTE. Those two components are directly correlated to CTE. So CTE was first discovered in the 1920s, and it was first examined by a guy that was just researching boxers and how they'd exhibited dementia at a young age, younger age than most typical clinical data. Now, in 1949, a neurologist named McDonald Critchley wrote more extensively on punch drunk system and characterized the neural degeneration of boxers, and it created that first link between CTEs and repeated blows to the head. And now, more recently, there's a huge gap within the research timeline of CTE. But in 2002, Bennett Omalu, he examined former NFL players and their brains and recognized the link between the head trauma they had experienced and neural degeneration. 3 years later, at the University of Pittsburgh, Omalu published findings on CTE in brains of more players who had recently deceased. And this is kind of what started the whole debate on, should people play football? Should my kids play football? And it led to the production of the movie Concussion, and how the NFL owners, as well as the commissioner, had been shown data and the link between head trauma and CTE, and they just ignored it. So now, more recently, Dr. A.C. McKee at Boston University has been doing a great job of researching more evidence on pathology of prevalence of CTE, not only in athletes but in all types of individuals, military, victims of abuse, accidents, and whatnot. So when you have CTE, you're going to experience a lot of physiological changes. So refer back to the image. The corpus callosum is a lot thinner. You're going to have a lot of atrophy in the frontal and temporal lobe, and so that's going to affect your ability to remember and to judge and plan. Your lateral ventricle and your hip is going to be enlarged, which is weird because most everything has shrunk, but it's going to enlarge due to the inflammation, as well as a lot of it's trying to get rid of a lot of that extra stuff in your brain. Your hippocampus is going to experience a lot of atrophy as well, and then the amygdala, which is associated with your fear and emotions. But the atrophy is not exclusive to these areas. It is widespread. So when you experience multiple subconcussive hits, you're almost guaranteed to experience atrophy almost everywhere due to the the force that's causing the brain to bounce around in the skull and move around in the cerebral spinal fluid. So this shows like kind of all the different components, but to highlight the two specific ones. The amygdala, fear and emotion, and then the hippocampus and memory. So one of the main takeaways from a lot of the research involving symptoms and treatment for those players that were before they had died, they'd experienced a lot of lack of emotional control and a lot of memory issues, and that was due to these components right here. They experienced so much atrophy that they just decreased up to 10 times their normal size. And these men were like 40 and 50 years old, which is insane to think about, that they were unable to remember things and unable to control their emotions, and that they were like individuals with dementia and Parkinson's disease. So in the diagnosis, there's no way to currently diagnose CTE because it's very hard to just cut open a skull and look at the brain while the person's still alive. So the only way that they're able to diagnose at the moment is post-mortem. Now, there's no biomarkers currently able to display CTE risk factors, but there has been some investigations into PET tracers, which positron emission so PET tracers, yeah, the positron emission, they take a specific radioactive radio label and send it into the bloodstream, and that goes into the brain, and see the aggregation of tau. So this right here is going to be a very important avenue of research in the coming decade, because they're able to see the aggregation of tau in a live person, and tau is a very important component, like a very important smoke signal. It's almost the fire itself, but whenever tau aggregates, you're able to diagnose and foresee a lot of potential problems, because aggregating tau leads to apoptosis. Now this is just kind of like an examination of the decrease of the size of the brain, as well as use of PET tracers to examine aggregated tau. So in a control group, not a lot of tau, but as you can see, it can become very prevalent throughout the brain. Now with CTE pathology, there's 4 stages of severity, ranging from tau proteins being very small clumps to larger protein clumps to severe atrophy throughout the brain and very, very aggressive symptoms. And what separates CTE from other neurodegenerative disorders is it has observable progression. So you're able to see someone at stage 1 and differentiate them from stage 2, 3, and 4. Another important component of the pathology is the brain weight is reduced. If you refer back to the image before, their brain is just decreased in size due to the atrophy. And then on top of weight change, there's significant neuron loss. So in the first stage, in terms of symptoms for the first stage, you're going to experience a lot of ADHD, a lot of dizziness, a lot of headaches. And then the second stage, you're going to experience more of the memory loss and the impulsive behavior. Now these stages right here, they're very closely linked to one another, but they do have distinct differences in the neuropathology. And especially with the second stage, if you're experiencing memory loss and impulsive behavior, that's because it's your amygdala. Your amygdala has experienced a lot of has experienced some atrophy, as well as the hippocampus. Now, as in right here, it's just like you're having some issues with connections in the neurons. In this stage, you're going to experience more atrophy within the brain, and that means tau has already been disengaged, and it's already aggregating, and apoptosis has already begun. Now, the third stage and the fourth stage, these are also very closely linked, rather than they're more closely linked to one another than the other two, and that's because you're going to see signs of dementia, and the beginnings of the real scary things that CTE can bring to a person. Now, what separates these two is the degree of atrophy. So this has medium atrophy, I would say, and then the fourth stage is going to have severe atrophy, where if you look at the brain, and it's going to be at least 30% smaller than a typical adult brain. And that's just due to the amount of apoptosis that occurred. So the mechanism, it's a very procedural mechanism. It's very similar in other tauopathies. So your brain, for the first step, you're going to experience some swelling and some minor symptoms as a result of impact. So think about like an initial concussion or an initial period of time where you're having a lot of hits to the head. Now, the tau proteins at this time are still attached. They're still attached to the microtubules, and you're still able to experience some kind of function. But then the tau proteins become disengaged. The next step, typically what occurs is there's more subconcussive impact, and the proteins begin to fall off and aggregate. And this is the second step, but it is a very, very long step and a slow step because the tau proteins will just there's no true identifier as to how much force or how much impact it takes to remove the tau protein, but it will happen over time. And so now, once these tau proteins fall off, the next step is they begin to aggregate, and they produce NFTs, or neurofibrillary tangles. And now, this is because they get hyperphosphorylated, and it just saturates all the active sites of the tau protein that are typically used to bind to the microtubule. And now those phosphate groups are bound to that protein, and it just makes it insoluble. So it's just a big old clump of tau just hanging there, and your neuron can't do anything with it. So the large pool of unbound, insoluble tau begins to start inhibiting microtubule function, and thus inhibiting optimal neurotransmitter function, cell signaling, production of ATP. All those are beginning to show signs of dysfunction due to the disengaging of the microtubules. And so at this time, neurotransmitters, ATP ions, are no longer able to travel down the axon due to the microtubules not functioning. And because of this, whenever you don't have energy molecules like ATP or electron and proton carriers like NADH, then your ion channels that dictate the flow of sodium and other important ions in the neuron are no longer able to regulate that. So in a normal neuron, there's going to be an electrochemical gradient where there's going to be more positive protons on the outside, and then it's going to have a more negative electrochemical potential on the inside. And whenever that changes, that's when you see usually a electrochemical potential, and then the cell's able to communicate. However, in this instance, it's not large enough to where that electrochemical gradient is broken, or that threshold is broken, and so it just allows the leaking of different ions to overflow in the cell. And one in particular is calcium. It begins to flow into the endoplasmic reticulum. And so the ER, the calcium goes into the ER, as well as it also floods into the mitochondria, and it releases apoptosome. And this is one of the main activators for cell apoptosis. Another one is caspase. That one is released whenever calcium enters the mitochondria. And so apoptosome and caspase, both whenever they begin to be present within the cell cytosol, that's when you're going to start seeing apoptosis. And then when that happens, neurons begin to die. Connections within the brain cease. And so then you just no longer have a connection between those components of the brain. And then the apoptosis begins to progress even further, and that's how you get the severe symptoms of CTE. So what are the metabolic consequences of CTE? Now, we've talked a lot about how CTE works, but we haven't talked about anything about like what happens to your metabolism whenever CTE occurs. Now, since if you think about it, the axons are no longer able to transmit signals, no longer to transport cargo to and from the cell body to the soma, as well as you have a lot of cells dying. And so that creates a very unstable environment for the metabolism within your brain. And so this inability to transport resources makes it very hard for your neurons to generate ATP. And without ATP, you're not able to regulate those ion gradients, because some of those channels and those facilitators that are important gateways for the cell, they no longer have ATP to power it. Another important factor in metabolic consequences is the brain metabolism is dependent upon glucose and glycogen. So if you're familiar with other sources of energy within the body, they can use fatty acids, they can use proteins, they can use ketones, they can use all different sorts of different sources for energy. Whereas the brain, it has the blood-brain barrier that prevents that. And glucose and by extension glycogen are the only way for the brain to have energy, because whenever you have glucose, you go through glycolysis and then you get your ATPs. And so it is super dependent upon that. Also, electrons and protons essential for the electron transport chain in the TCA cycle. Those are no longer transported. So think about NADH and FADH2. Those two components that are very important in both of those cycles are no longer able to be transported. So they just sit there. And that inhibits a lot of metabolic functions within the body, or within the brain. So another important thing to consider is when you have less neurons, you're going to have less glucose in the brain. So when you have a lot of severe atrophy, it's going to reduce the amount of glucose that's able to enter the brain. And that's an overall less amount of energy that your brain has to use and to communicate, to plan, to reason, to move your muscles, to regulate the movement of your muscles. And so this is just an important basic concept. When you have less neurons, you have less glucose transporters. When you have less glucose transporters, you're going to have less glucose that is available for your body to use. And so it's been shown that CTE and TBIs, and by extension CTE, are they're linked with decrease in complex 1 function of the electron transport chain, which is essential. That complex right there starts the whole process of oxidative phosphorylation and then the subsequent creation of ATP. And so complex 1 is no longer activated. It is inhibited whenever there is an increase in tau. So those concussions, those subconcussive impacts that release that tau from those microtubules, that's stopping the mitochondrial process, or the mitochondrial's energy production process. And so this consequence is due to the tau just becoming aggregated, insoluble, aggregated, hyperphosphorylated, and it's no longer able to go through those metabolic processes. So in essence, your metabolism, it doesn't cease because there's other neurons, but in certain locations it ceases to function. And that's why you see a lot of issues with people that have severe cases of CTE and other tauopathies, is because they don't have enough glucose providing energy within their brain. So some treatment and research. So there's currently no treatment for CTEs because it's one of those things where it's really hard to stop it once it gets started. So a lot of the treatment is for the symptoms of CTE, so the dementia, the depression. A lot of times they use SSRIs. Another thing as well is some of them develop motor neuron diseases, and then they'll use specific drugs to alleviate the tremors and other symptoms that come with it. And at this time, medical professionals are they're putting more effort into advocating prevention over cure, and this is good because But if you don't want a problem, then don't get yourself into a situation to have that problem. But at this time, that's not feasible, and so more effort is being expended upon to find cures, or at least therapies that can decrease the amount of neurons that are decrease the amount of neuron loss, decrease the amount of tau aggregation, as well as ways to reattach the tau to the microtubule. And because of that, as a consequence, you're going to have more metabolism. You're going to have more ATP molecules flowing around. There's also not a lot of reliable ways to diagnose while the patient is alive, and so that causes a lot of issues because you can't find the proper time for intervention. But more, as we discussed earlier, PET tracers, as well as MRIs and fMRIs, are being used to help diagnose, or at least examine more closely, some of the symptoms that individuals would have with CTE. Some more therapies are NAD plus intravenous therapy that aids in ATP production. The introduction of an enzyme called sirtuins, they aid in neuron growth. And then omega-3 fatty acids are going to help with repair of neurons and myelin sheath. And then they also have a lot of metabolic fates within the brain, and that can aid or jumpstart some of those processes. So that's just some typical research some new research that's being conducted at the moment. So what's next for CTE? What's the next thing that we got to do? So we need to find a way for in vivo diagnosis. So that way we can examine the problem before it gets worse. We need to find ways to repair microtubules, or find an answer to, can we do that? Are we able to repair microtubules? Are we able to reattach that tau? Or is it impossible? Another thing is, how can we reduce the scale of apoptosis? Can we limit the amount of neurons that die so that the patient has enough connections within their brain still functioning? Another thing that's going on currently with a lot of the Heads Up program for football and other sports is, how can we prevent as many TBIs as possible? How can we protect the brains of individuals? And another thing too is using tauopathies like Alzheimer's disease, motor neurons disease, Lou Gehrig's disease, Parkinson's disease, and other neurodegenerative disorders. How can we use some of those drugs and treatments to affect CTE? Because a lot of them have components of tau, or a lot of the issues that they have are due to tau proteins malfunctioning and microtubules malfunction. Of course, there's also other things like SOD1 and TDP43, but those are they aid in the main diagnosis, but tau also plays a role. And that is it. I would like to thank you all for taking time to watch this. Again, my name is Zach Cox. I am a graduate student at the University of Kentucky, and this is the conclusion for my graduate school project for CHE 552. And you guys have a great evening.